Welcome to Cinematic Ocean Effects in Houdini. My name is Al-Tobi and I'll be your course instructor in this journey. I've been working in effects the past decade and a half of my life, and I've had the chance to work on big blockbuster movies, TV shows and commercials. And a lot of that work has been in effects in Houdini, so a lot of that has also been water effects, which is the topic of this course. If you want to follow me, you can find me on my own YouTube channel, and you can find me on LinkedIn, and of course on Voxside.com and this YouTube channel. Now I want to give you an overview of the chapters we're going to have in this course, so let's jump in and do that. Now, before we jump into the different chapters in here, I just want to say that this course is meant to be for basically everyone, really. Even if you're new to fluids in Houdini, this is the course that takes you from learning the basics of the fluid solvers or the flip solver up to an advanced level. But it's also meant to be for those that know a bit but want to advance their skills. So all you need is some fundamental understanding of Houdini, and then we take it from there to build upon that to learn some simulation methods. So let's jump into the first chapter in here. And in this first chapter, it's basically what you're looking at right now. It's the introduction to the course. And I'll show you some settings I have in my default Houdini desktop and some other bits and pieces to set up the project. So this chapter will be the quickest chapter to go through. So that's the first chapter. The next chapter is the important fundamental chapter. This is where we learn the basics of volumes in Houdini, what a grid volume is, what a VDB volume is, and what a field is, and so on. And once we know the basics of volumes, we go further to look at some theory for how flip solvers work in Houdini and the physics behind the fluid motion of fluids. And then at the end, we'll look at how we can take that theory and put that to use, where we'll create a flip solver from scratch. So if you know a lot about volumes in Houdini, you may want to skip a few episodes to the theory about flip solvers and fluid solvers in Houdini, and then how to implement that in the dynamics network. So that's the second chapter, which is a very important fundamental chapter of this course. And if you're watching the free version of this introduction to the course, you'll get this chapter for free. So that's the chapter you're probably looking at. So that's chapter 2. And the next chapter is where we jump in and start looking at some of the tools in Houdini. The first set of tools in this chapter is the ocean tools, where we'll look at the ocean spectrum, the ocean waves, and some of the other ocean tools in Houdini. We'll go through the parameters and the settings in the spectrum node, and we'll see how we can adjust it to get a look to get bigger oceans like this. And you can see we're talking about the different features in that node. And then we'll look at how we can art direct our own waves through the ocean wave node. And then we'll look at some more detailed settings that we will be using later on in this course. So that's chapter 3. And the next chapter is a bit more comprehensive chapter about the flip solver in Houdini. In here, we'll go through almost all of the settings in the flip solver, and we'll test multiple settings to see how we can use that later on in our main shot that we'll create. But this is where we also test multiple things that might be useful for you, like viscosities and divergence and air incompressibility and densities and so on. So we'll use this as a way to create a test bench for us to test different settings that we will use later on in our main shot. So this is a very cool and important chapter. You'll see a lot of different looks and different dynamics using the flip solver. So that's chapter 4. Chapter 5 is where we start looking at the actual shot we'll create, which is the this main shot in here, the cliff interaction with the fluid. And in here we'll start looking at setting up the collision, how we can scatter it around, and how we can optimize it for rendering and for collisions later on based on the camera and some more advanced ways of optimizing your geometry. This is also where we'll create the ground below the cliffs. So this is essentially just preparing the environment and the collision for our next steps. We'll also create the camera just so we see what we should optimize and what we should keep in our collision. And later on, we'll use this camera for rendering. So that's chapter 5, which is the initial part of this shot we'll create. And then we'll jump into chapter 6, where we'll be setting the flip settings for this shot. So in here we'll dive in and use some of what we learned in the previous test bench and previous episodes to customize our flip settings, to create some custom collision forces and collision behavior around the cliffs, and generally direct our simulation as we want it to be. After the flip simulation is properly set up and done and simulated, we'll jump in to create a surface out of that. So we'll start by converting our volumes coming out of the flip solver and the particle field to a VDB volume. And then we'll process it and try to add as much complexity and as much detail in there as possible. And then at the end, convert it to geometry, which I don't think I have a picture of in here, but it will be a detailed surface geometry. We'll also look at removing what we don't need in this surface. Like on the collision, you would probably have some faces in the surface that's kind of below the surface, but they are hugging the collision cliffs. So we'll do procedural ways of masking that and removing all of that we don't need. So this is essentially just getting our flip simulation set up and finished before we jump into the next chapter, where we'll start looking at the whitewater layers. This is the biggest chapter we have, chapter number 7. And we'll start the chapter with some theory before we jump in to see the built-in whitewater solver in Houdini, just to see what that gives us by default. And then I'll explain why we will not use that, and instead we will build our own custom solver to create the whitewater layers. So yeah, in here we'll be creating multiple layers, about 4 or 5 of them. And then we'll also have a wet map where we'll have all of the particles interacting with the cliffs, generate a wet map based on a custom UV we'll create for this cliff, and then we'll bake that out to a texture map. I'll also show you some of the techniques that's used in the built-in whitewater solver to add to our custom solver to get some complexity, where we get different layers of looks in the whitewater. We'll also have a custom bubble field or bubble particles underneath the surface. So this is a very long chapter, but it's a very important chapter that will determine most of our look of the ocean. We'll also actually create a wind field that will be piped into the whitewater particles so they can flow with the wind in here. So yeah, that's chapter 7, the biggest chapter we have, and it's going to be a very cool one. After that, we'll jump into the stage context, where we'll start setting up our rendering. But before we jump into that, we'll actually create some vegetation, or use some vegetation in our cliffs. So we'll try to find where there is green regions in our cliffs based on the texture map. And using that, we'll scatter some instances of grass, as you can see in here. And we'll add some additional hero vegetation elements with some custom fake wind that just flows, just to add some more realism to the shot. So once that's done, we'll import everything to the stage context and start setting up our layers. We'll set up our custom wet map shader. As you can see in here, it's darker and more reflective in this region. And then we'll start looking at the ocean layers. So we'll do a custom shader for the ocean surface with some whitewater elements in here. And then above that, we'll start adding our whitewater layers. As you can see in here, I believe that's the thick foam. And then you have the general elements in here. And then you have the overall added layers in here, I think. So yeah, this is where we adjust shaders and just add everything and make everything ready for render. And then we'll dial in our render settings in Karma. We'll create the AOVs we need for our render, and then send off our scene to finish the render. So that's chapter 8. And then at the end, we have chapter 9, where we'll look at compositing all of these layers into a final image that looks a bit more realistic than what's coming out of the render. In here, we'll look at adding some additional lens elements, and then we'll add some more lens effects just to emulate a real lens in our shot. We'll utilize some of the AOVs, like the depth and so on, just to add some more interest to our shot. So we'll basically just finish the look in here, and I'll show you some smaller bits in DaVinci Resolve as well. But in addition to this shot, I'll also show you the shot that I have in the promo video, where we have a camera very close to the ocean. This is a very simple shot, so I'll show you the Houdini file for that and the nuke compositing file for that as well. And I'll show you how we render a simple surface in here with some spectrum displacement. And then we'll use the background HDRI to add some wrapping lights in compositing and do some depth of field in here. And that's essentially the whole 9 chapters of this course. We'll go through a lot. It's about more than 17 hours of material, and you'll hopefully be very versed in knowing how to deal with fluids in Houdini. Great. Before we jump into the first chapter we want to look at, I just want to say that this course is for everyone, but I do have a very powerful hardware on my machine. I do have a powerful CPU and GPU, and I have a 128 gigabyte of memory, so I may have more capacity than your computer. Keep that in mind. Now, saying that, you should be able to follow this course in any amount of memory. If you have 32 gigabyte or 64, it should be fine to follow, but you just need to reduce the resolution, which I will talk about in a later episode. But yeah, it's possible to follow along. You just need to make sure that you don't have too high resolution or too many particles in your simulation. Great, let's jump into the next episode. In this episode, I just want to talk about the included exercise files. So if you download the exercise files, you'll see that you have 2 folders inside them. You have the Houdini elements and you have the nuke elements. So in the Houdini files, you will see that there is 2 folders. One for geometry that I've added, like the cliffs and some vegetation that we will add later on in the course. And all of them also have textures inside them, and they have their USD file, as you can see in here. I think the cliff in here is an FBX file, which is a bit different than the other ones. But that's the geometry. You also have the textures, which I've added some extra textures that we will use in the course later on. The HDRI map and the texture we can add to the shore ground later on. Now, each of the chapters in here and each of the episodes have their own file, Houdini file, and you can open each of them and see what we've done in them. They should be mostly accurate. There's a couple of them that have a bit more than what we showed in the episode, but overall they should have what you expect in the episode at least. So this will be a good way to follow along if you get lost and if you're not able to set up the scene as we do it in the videos. You can essentially just go in here and open that file and look at what we did. Obviously, if you open the last file, you would see that the whole scene is done. So you can basically look at the final setup. I've also included the close-up shot with the ocean as the main element or main shot we work on in these chapters is the cliff shot, but I've included the other one and I explain what this is in the end. So that's the Houdini exercise files. And you also have the nuke elements or nuke files. So you have 2 scripts. You have the main comp for the cliff shots, and then you have the extra additional close-up shot of the ocean. And I've also included some textures or some files in here for some lens effects or lens droplets that are out of focus that we can use in the compositing stage. And that's it really for the exercise files. Make sure to use them when you need them. Thank you. In this episode, I'll walk you through how I set up my Houdini so you're not confused why yours is looking a bit different. So when you start Houdini for the first time, it's looking like what you have in front of you right now in this window. This is, by the way, on a Windows machine. I will also use a Mac later on when I go through the main setups in Houdini. But I want to show you on a Windows machine as most of you probably are using a Windows operating system. So the first thing I usually do when I set up a new Houdini desktop is to make this network view where we set up our nodes to be a larger part of our desktop. So I want it to be larger here, so we have a lot more real estate for our nodes. So let's do that. I'll just drag this here to the middle somewhere. And I will just close these windows in here like this. Make sure this is in the middle. And now we have a larger network view for our nodes. So if we, for example, put down a geometry node, we have a lot of space in here. If you want to get your parameter settings, as we don't have them right now, you can just press on P on the keyboard and you will have your settings in here instead. And you still have a large network view in here. So press P again if you want to remove that. So P. And I also like to have a grid on my network view in here, as right now it's just blank and it's hard to know where to place your nodes. So if you go to Tools in here and go to Grid Lines, you will have a grid to easily snap your nodes to. I usually like to make this grid a bit smaller. So if you press D on the network view, you can scale this grid down in here. You can do 1 by 1, or I usually do 0.5 times 0.5. And as you can see, the grid is a bit smaller. Next, I like to take away these shelf tools in here, because I don't usually use them and they're taking a bit too much from the size of the window. So I'll keep this closed. In the viewport, I'd like to do some changes. First of all, I usually deactivate the materials in here, so I don't want to see them in the viewport. And I will also deactivate the light, or just put it to work lights, just to make it a bit simpler. And in here, I would like to hide other objects in the world space, as if you have multiple of these nodes in here and you go inside of them, you don't want to see the other nodes in the object view in here. I'll just delete these. Next, I would like to change the viewport a bit more. So if I press on D on the keyboard on the viewport, there's a few settings here we can change. I usually start by going to the scene tab in here and increasing the anti-aliasing samples to have a crisper viewport. And then if we go to the texture tab in here, I usually increase the 3D texture limit to 512, as that will give us a crisper rendering of volumes in the scene. But this is just for the viewport, so it doesn't matter at the end in the rendering. Then I'd like to go to background in here and change the background to be dark. And if you put down lights in the viewport and you add an HDRI image and you don't want to see the HDRI image, I usually go in and deactivate it in here. So to remove the HDRI image from the viewport. But right now I'll just keep it as it is. Let's save this as a default. Press OK. And this also saves these settings we changed in the sidebar in here and the top. Great, I'll exit this. Next, I like to reduce the size of this play bar in here. It's very large, as you can see in here. You can reduce it to half of its size by going to the file in here to the edit and going to preferences and general user interface. And then you can change the play bar UI in here to compact, and you can apply this. So next time I launch Houdini, this will be a smaller size. In here, we can also set a startup desktop. Right now it's on build, which is the default desktop. But we want to save whatever we did in here to a new desktop and apply it in here. So let's do that quickly. So if we go to the build up here, and then go to save current desktop as, and you can just call it something. I'll just call it creative. And then I'll press save. And that's saved. And now I can go to the edit and preferences again, general user interface, and I can go to startup desktop to be the creative I just created. And I can apply and accept that. Now, there's a few default settings I have on a couple of nodes. So if we just jump inside this geometry node I created, and if we put down a group node and take a look at this, I usually keep the name to be $OS. And $OS is an expression in Houdini which takes the name of the node and put it to be the group name. So if we just create a box in here quickly and connect it in here, you can see the name of the box. If I just click on this node, you can see it's called group 1. If I change this to box or box 1 or box 2, you can see the name of the group is changed to whatever I call the node. So this $OS expression is just taking the name of the node and putting it in as a name for the group. So the way to save this is to go to the cogwheel in here, and you can go to the legacy presets, and you can save as permanent default. But be careful what you save, because whatever you change in here will be set up to be your default every time you create this node. So I would only change the group name in here. Next node I usually change is the file cache node and labs file cache. So the file cache node, it's storing the caches directly to the hip directory and under a folder called geo, which is good if you have a large hard drive wherever you're creating this hip file. But for me, I'm using an external drive only for caching. So what I usually do is I set up a variable in Houdini that will recognize the path to my drive every time I start the Houdini session. I call it $cache drive, and it's not working right now. You can either go into the edit aliases and variables and set that up in the variables in here. So I can, for example, write the cache drive in here. So if I just give an example, if I just write test in here and give it a text, hello world, and if I save this, if I close this, and I will just call in $test, that will, if I middle click on this now, it will give me hello world. So I can save that. I can create variables that are recognized in Houdini in this session by going to the edit and aliases and variables in here and adding that in here. But the cache drive is not something I want to do every time I start Houdini. So what I usually do, I go to the documents for Houdini. So if you go to your Explorer, File Explorer, and go to Documents, you usually have a Houdini and then version of Houdini you have. And in here, you have a houdini.env file. You can open this with a notepad. And in here, you can create your own variable that will always be recognized by the nodes in Houdini. And in here, I can, for example, say cache drive equals E:, which is the path to my external drive. And that, if I just save this now, Control Save, and close this and restart Houdini, this will be recognizing cache drive, which it doesn't right now because I need to restart Houdini. But this is just the drive name. I also have a $prj, which stands for project, and this is something I usually set up for every Houdini session. So this will be the name of the project. So if I just write prj in here in the variables, and I'll just call this, for example, cinematic oceans, that will be what I get in here in this as a subfolder in this external drive. And you can do /geo if you want to keep it clean. But I'm just showing you this so you know why I have this path in my file cache, so you're not confused why I have it. You don't have to do this. This is how I set up my storage at home. And that should be it for having a similar desktop as me and similar saved defaults for my nodes. Now, before starting any project in Houdini, I usually like to set up the folder structure or the project folder for this project. And in Houdini, there is a way to do that. You can go to the File button and you can go to New Project in here, and you will have this window where you can type in the name of your project and the destination or the path to the project folder. So let's call this, for me, it's going to be Cinematic Ocean Course. And I'll just choose a destination for this quickly. Let's go in here. And in here you can also choose the folders you will have inside this new folder that's going to be created. And these are the defaults, and you can add additional ones if you want in here. I'll keep the defaults and press accept. And the reason why it's a good idea to do this is we have a folder structure. Let me just get it up in here. So this is where we created this folder, and inside it you'll have many folders. And all of these folders will be easily referenced whenever we save our HIP file in here, because you can just use a $HIP expression, which takes you to the folder where the HIP is, and then you can access all of these folders. And as I showed you on the previous episode, that the default settings on a cache node is a $HIP storage folder. This is where it goes. It goes to $HIP and /geo. It saves here automatically. But if we, for example, wanted to add textures that we will read in later, you can add them in the texture folder in here. And in Houdini, you would just go in and let's just create a geo node, and let's just add a grid. And if we just do map from attribute from map, and in here, if you would load in a texture, you can go into $HIP, and you can do /text, and then find your texture, whatever it is. So if you just open this now, oh, I think, yeah, we haven't saved our HIP file yet, so you need to save your HIP file. So let's save as. Yeah, this will also give us a $job, which also takes us to this this folder structure we created. And I'll just call this chapter 1, episode 4, and I'll just give it a version 1, and then I'll save this. And now this HIP/texture should also work. As you can see, I don't have anything here right now, but it takes us directly to this folder structure, which is an easier way to read in files or save files. Great, now we have this set up. Let's continue. Welcome back to chapter 2. In this chapter, we'll look at some theory and some methodology and just generally what's important in this course. I also would like to take a look at a couple of references, and I can show you what I aimed for when I created the final image. So to begin with, I just want to take a look at a few references in here. This one is from YouTube, and all of the other ones are on the internet. And let's just play this quickly. And it's very important to look at real life references to see how the dynamics of whatever effect you're creating, how the dynamics is in real life. And in this one, you can clearly see the weight of the water, the mass of the water, how heavy it is, how much it's moving in energy, and the different layers you see of white water. So we have some thick white water, we have some thinner strands, we have some windy particles, and so on. As you can see, this one is beautiful. So let's just pause this somewhere, or actually let's start with this shot in here. So in Houdini, we have fluid solvers that do a lot of the work for us, but they are never a complete solution for the final product we want to create. That goes with all of the tools in Houdini. They will get you a certain percentage to your final product, and then you have to use your creativity to extend that to a 95, 98%. You're never going to hit 100%, but you try to get it as close as possible. And in a reference like this, you can see that, for example, the white water has some thicker bits in here, and you have some thinner elements in here, and you have some elements inside the water, and then you have some foamy bit in here. And if we play this forward, we can see how much bubbles and white water there is inside the surface, just right underneath the surface. You can also see the part that has sunk down a bit further below in the surface. If you go back to the previous reference, you can see how the water takes a lot of time to fall down to the surface. It's both heavy and light at the same time, so it flows with the wind and the atmosphere, and it also keeps a constant gravity falling down. We need to keep in mind all of these, and you can see even in the hits, there's chunks and there is finer bits that are just floating with the wind. Let me find a good frame for that. In here, you can see there is chunks in here, and there is generally finer bits that you see in the splashes. So all of these are different elements that we need to combine together. We can't expect the Houdini setups that are pre-built in Houdini to do all of this for us. So we need to kind of divide this work into multiple sections and then combine it at the end to get this beautiful final look that we're going for. Looking at references generally helps a lot, just to get an idea of what you should aim for. It doesn't have to be exactly like the reference, but you should kind of augment some of the elements you see in here. Let me show you another clip in here. You can see in this one how the wind is taking the whitewater. And you should look at references to kind of have an idea of how much of each of these elements you want. This is very cool, but I think this is a bit too windy, because when you create something like this and if you have this much wind and you have some other vegetation in the scene, everything should be affected equally. So you can't have a few static trees and a very windy ocean. So keep that in mind. Try to balance things out at the end. When we are going to set up all of this in Houdini, we have to keep in mind one thing, and that is, especially generally in VFX, when you try to work on entertainment that's going to be presented to the masses, you have to keep in mind that the final image is the important thing in here. It's not the Houdini setup that's important. It's not how cool the setup is. It's not how cool your code is. It's not how cool your solver setup is. So at the end, we have to keep in mind that the final image that we're going to present, that is the most important part of this. So whatever we create in Houdini, always keep in mind, okay, how is this going to look at the end in the final render? Now, saying that, we will be diving into some technical bits, obviously, as we were using Houdini in here. So we will be looking at technical setups and advanced way of setting up oceans and stuff like that. Now, I also want to touch on in Houdini, so let me just open Houdini, that you all probably don't have the same spec on your machines as I have on my machine. I have two computers in here. One is a Windows desktop and the other one is a Mac. I'm currently using the Mac. Both of them have powerful CPUs and GPUs, and both of them have 128 gigabytes of RAM. So keep in mind that my spec might be a bit better than yours or more powerful than yours, or vice versa. Maybe you have better than mine. So if you have less memory, generally like 32 gigabyte or 64 gigabyte, then keep in mind that the resolutions that I set up in the VDBs, for example, or in the let's say we have a dot network. We'll go through this later, but if we have a flip object in here, the resolutions in the particle separation, this determines how many particles you have in the system and how high resolution volume you have in the system. So if your computer is struggling, try to go up in number in here. If you go too far down, then your machine might be struggling with this. Now, saying this, you have to keep in mind that changing the resolutions in the solvers in Houdini will change your result a bit, so it would not match 100% to mine. Usually the forces would be not as powerful or not equal in lower resolutions compared to higher resolutions. So keep that in mind. Great, I think we'll end it here and we'll continue with other bits in the next episode. In this episode, we'll look at some basics about volumes and fields. in order to later understand how a fluid solver works in Houdini. This is basics, so if this is too simple for you, you may just skip and go to a further episode. So yeah, we'll look at volumes, fields, SDF, and VDBs. So just to understand what a volume is, we have to look at start with a 2D plane. So a simple two-dimensional image is a result of pixels. So just like this grid we have in here, you have pixels that represents where the information is. So just to give you an example, let's look at this test rubber toy in here. If we would take a slice of it in the middle and just look at it from the side as an image, it would look like this essentially. This is a low resolution representation of that image. We can increase the resolution just to test this, like this. And as you can see, it's a representation of the cut or the slice in the middle of that geometry. And we can see where there is information and where there's no information. Just like this 2D image, a 3D image, or a volume in this instance, is a stack of these 2D slices put together. So let's look at a visualization of how that could look like. And I'll just lower the resolution a bit, as this is a bit too high. Just like this, we have a three-dimensional image of this rubber toy in here. So this is how it looks like. Right now we're seeing both the negative space and the space with information. I've just made a tool in here just to scale down the empty bits. And as you can see, we have this three-dimensional representation of these pixels for this rubber toy. So this is a volume, and a regular Houdini volume would have information. So even if this bits that are empty in here look empty, they still have information of voxels. So there's still a voxel that says that there is no information in here. A voxel is basically this cube. So one cube here is a voxel. So instead of a pixel in a two-dimensional space, you have a voxel for 3 dimensions. So although these voxels are empty around here, this is still stored as a complete volume. That's a complete box in here. And I've made a representation of this in wireframe for you to take a look. So this is a 2D image, and this is basically a 3D image, and that's a volume. A volume is also a field. A field is basically a volume of information. Just so you're not getting confused by that in other Houdini setups. So it's basically the same thing. We'll look at what you usually have in a field compared to a regular volume. But basically we tend to use fields inside a simulation, while when we are in a geometry network like this, we call them just volumes. All volumes and fields have properties that tell you what they are, and their resolution and their size and so on. So if we go up to this ISO offset in here, which creates, which takes this geometry and makes it into a volume, and in here we have a division size, which is basically the size of each voxel in this grid. If we middle click on this node, we can see that it says it has a name. It's called density, which we've given to it in here. And it has a voxel size of 0.05. And it also has a resolution, which is basically the size of this cube divided by the voxel size, gives you the resolution. So we have 3 axes. the x-axis, the y-axis, and the z-axis, and all of them have 20 in resolution. And then you have the active voxels, and then you have the data type. Data type is essentially whether this is a black and white mask, or if it has a multiple dimensional floats or masks that can be combined to be other attributes or variables. And it also identifies the type to be just grid, which is the regular Houdini volume. And if you see in the point amount and primitives and vertices, it only has one in each of them, which represents that there is one volume, so it doesn't care about the voxels in here. The information about the voxels is in the volume down here. All volumes have a name attribute included to know what the name of the volume is. So this is a fog volume, and there is other ways to represent volumes in Houdini, and we'll get back to that in a second. So this is a regular Houdini volume. If we go to the side a bit in here, we can see a VDB from polygons that says VDB in here. This is another type of volumes in Houdini, and VDB is a sparse volumetric dataset. And what that means is that instead of storing the information of the whole box that we saw earlier for the grid, it only stores information around what it needs, which is more memory efficient and just generally easier to work with. It also has the ability to store only a few voxels inside and not the whole interior. And we can easily see that by just adding a VDB visualized tree in here. And if we just display this, and if we go to active voxels and solid boxes, you can see that it only has boxes around the region it has information, while a ISO offset has voxels everywhere, essentially. So this is good and very, very memory efficient. And this is usually what we use in most saved files for volumes. So that's a fog volume and its representation in boxes. If we go further to the side in here and look at this second VDB from polygons, you can see a different representation of this volume. It's still a volume, but it's an ISO surface. So what you're seeing in here is something called ISO offset, and you can see that if you go to this primitive node in here, you can change the adjustment visualization in here, and you can choose to show the volume as a smoke, or you can show it as an ISO surface, which is what you're getting directly in this VDB from polygons. So why is it looking like this? This is not a normal volume. It's as you can see in here, it's called a distance volume. It is basically a sign distance field. A sign distance field is essentially a volume that just tells you how far you are from the surface of a geometry. So we have this rubber toy in here, and this volume is just telling us how far we are from the surface in voxels. And we can see that if we go to this volume slice in here, actually if we go further to this color, we can see that wherever the surface is, it is dark, and the further away we are from the surface, the brighter it is. And the same thing above. The reason why it's brighter in the middle right now is because in this VDB from polygons, I have activated to fill the interior and not activate only a few voxels. So if I remove this fill interior, as you can see, it's not as bright, as you can see. You could add more voxels. So this is the voxels from the distance. So if you imagine like 3 voxels in here, this is how much data it's using right now. So if you increase this, you can see it's getting brighter. And the same thing on the top. That's because it's storing a higher distance to the surface And we can look at this even further by going to this visualize in here. And if we just activate the grid points in here, as you can see, wherever we are very close to the dark region, it's almost 0 in amount. So that's the distance to the surface. And if we go further, it's getting higher. So we are in the minus 0.05, minus 0.07, and so on. It goes higher and higher. Obviously, this is in the minus because we're inside the surface of this rubber toy. If we go outside, it is in the positive, as you can see in here. And this is extremely useful and a tool we will use a lot throughout this course. From this representation, this sign distance field, it's easy to create a surface again. So we can do a VDB convert, for example, and just convert this back to polygons, and you see we have polygons that comes from this volume. Obviously, it's not as accurate as the coming in volumes. That's because the resolution of this volume is not that high. So if we increase this to something like 0.005, you see it's a sharper image, and we convert it back, it looks very close to what we had before, like this. So this is very useful. See what I have in here as well. Yeah, so let's just lower the resolution again. We had it 0.02. And let's lower these voxels to 3 and 3. As you can see, that's how much voxels are stored in this VDB, as it's very efficient. It's not storing all the voxels in a cube, only the ones needed around the geometry. And you can extend that by changing these bands in here. If you go to this primitive again and change this view to a smoke, you can see that we're seeing this sign distance field as a smoke, but in reality, it is not. And the way you can understand if it's a smoke or not, you can show it as a smoke, and then you can display the voxels. And then you can see the voxels are only inside and not outside. That means that these outside fog voxels are not there really. So it's just a negative space. This is important, as you will see this in the fluid solver later on, but we'll get to that. In the primitive in here, or the visualization of this primitive and volume, you can also change this to invisible. That way you have a volume still in here, and you can see it's called surface, and it's a VDB volume, and it's a data type float, and this is the resolution. But it's not visible in the viewport. A few of the volumes that come out of the fluid solvers in Houdini are invisible, so it's important to know that you may have volumes included, but they are not visible. Cool, let's change this back to isosurface. Now all of this we've seen in here is a float volumes or scalar volumes. Essentially it's a volume with one value in each voxel. So each voxel has, let's show a voxel in here. So each voxel has, let's say this voxel in here has 0 right now. The one in the middle in here, let's say this one, it probably has something like 0.2. And then you have the one in the middle in here maybe has 0.9. So all of them have one value. And that value can be like it's a float value, so it can be like a long number, 5, 8, 5, and so on. Depends on how high precision you have in your float values. But it's only one value. So you can't store, for example, information about a direction to a place, or a position of a voxel, and so on. So it's just a one value voxel, basically. So if we go down in here and take a look at this velocity around visualization, I just want to make sure that we understand what a vector attribute is. So right now we're looking at a velocity. Let's imagine we have a point and we have a velocity that's basically a representation of a direction and a speed of where this point will go in the next step. So it starts here and we want it to end in here. And the value of where it ends is basically in three-dimensional space. So it's not only in this direction, it's not only in the y direction, and it's not only in the z direction, it's in all of them. And that's why we have a 3 float values to represent where it is in space, where it's going in space. And I can change that, if you see in here, to put it anywhere else I want it to go. And that changes the velocity we need to move it into this space. So this point needs a velocity attribute of these values to move in here. So how can we do the same thing with a voxel? So a voxel can also hold information about direction, like we saw in here in this point velocity. And for that, let's go to the side in here. We can look at this volume. Let's display it. And there's no information right now, but I can show you that it is possible to create a vector instead of scalar. So a scalar is essentially a float value, so one value voxel. And this one is a 3 value voxel, basically. And we can see that if you middle click on this now, you can see we have, instead of having one field or one volume, we have 3 different volumes that represent the direction of each of these axes for this velocity. And I've called it V in here to have it as velocity. So right now a voxel has basically 3 voxels to represent this velocity. But we can combine this and make it into one voxel that has a vector data. And we can do that easily with the changing to VDB. So I've changed this now to a VDB. And it's still 3 different values, but we can merge them together in here to become a vector volume that has a data set of vector, so 3 floats basically. And now in each of these voxels that we have in here, so each of these voxels, we have a space for 3 different values that we can use for different things. So let's take a look at that. So in here I'm creating a box, and from that box I'm just creating a bunch of points or particles or whatever we want to see them as. And in here I'm making these points into a volume, a VDB volume. So it's in here, and I'll just deactivate this for a second. And this is a volume of these points. They are very large right now because the particle scale is very high. So we can reduce that if we wanted to something like 0.2 or 0.3 and so on. So that's just the size of each of these spheres. And that volume is a velocity. I'll call it velocity. And I want to show it as a fog volume. And it's a type, a vector float. So if we middle click on this right now, we can see it is a vector. And it's 0.1 in voxel size, and this is the resolution. This now is just an empty velocity field, as we call it. So a volume of vectors that is right now empty. What we can do is add some information to these points. So right now they are empty, but we can give them, for example, a velocity. So if I just display this velocity in here, you can see we have like quite a random velocity based on this add curl noise. And we can change this swirl size if we wanted, like this. And now if we look at this volume, it's a bit different because it's very difficult to show a three-dimensional field in Houdini. So the way we usually do that is we sample. So we go back to these points, or any points we can have inside these this volume, and we can sample whatever value these have. So let's say this point in here will sample the volume at that position, and we will give it whatever value there is in that voxel. And there's an easy node to do that. It's called volume trail, and it essentially just takes a velocity volume and displays the trails of that. So now we can see our velocity in its motion. So this is a very good example of how we usually create wind in a simulation. So let's say you have like an ocean in here or something. You can create like a box around that ocean and give it a lot of voxels inside. So a lot of voxels in here. And each of these voxels have a certain direction of where they are pushing anything that's inside. And you can take that information and put it into the fluid simulation, and then you can make that fluid simulation so whatever splash you have will be affected by that wind, like this. Cool. So that's a general basics overview of volumes in Houdini. Obviously there's a lot more to cover, but we'll just go through a few more nodes in the next episodes, and we'll take it from there. Continuing from the previous episode, we can look at this volume trail or the velocity field we created. And I'd like to show you a couple of nodes, VDB nodes. To begin with, let's look at the VDB advect points. So you might hear us talk about advecting points or advecting particles a lot throughout this course. And just so you understand what it is, I'd like to show you this example. So we have our point cloud we created here previously, and we can use this velocity we created, velocity field, to move these particles in space, in position. So let's say this point in here would be moved like this one would be moved like this, and so on. And there's a node to do that at the geometry level. It's called VDB advect points. So we can connect this first input in here to the point cloud, and the second input into the velocity field in here. And if you display this now, you can see that the shape of this point cloud has changed. And it's doing it based on the time step in here. So one time step is basically 1 second divided by the frame rate you have. So we have if you go to the settings in here for the global animation, you can see that the FPS, frames per second, is 24. And this is read in here by the $FPS. So we're taking 1 second divided by FPS, which will give us this number. So this is how much it will move for each frame, as the velocity is basically how much movement you want in 1 second. So if you want to just see this working a bit more, you can just remove this channel, delete channel, and you can increase this. You can see the particles or the points moving based on this velocity, but they're only taking the initial velocity. If I just put this back to defaults, we can do this based on a step by step, just like a simulation, by just adding a for each number. And I'll just remove this, and I'll connect the beginning of the for each in here and the end of it in here. And I want this for each to take the result and put it back up here and do something and export it and put it back and so on. So it just loops the same result on and on. So we need to set that up in the settings in here. If you go to the for each end, you can go to the gather method. Instead of merge each iteration, we want to feed back each iteration. And the same thing in the beginning here to fetch feedback. So now if we display this, It has 10 iterations by default. Let's just reduce this. And you can see this is looking like it's simulated almost over time. So it's moving until the bounding box of this velocity field we created, as you can see. So this is basically advecting points. We're just moving points based on a either velocity field or some form of a velocity we're adding to the particles. You also have an advect, VDB advect, which is for advecting volumes. We don't need to look at this now, but we'll cover something like this later. So that's one node from the VDB toolset. And obviously we have a lot more of them in here to look at, but we'll just choose a couple more to focus on that will be needed later on. Let's go in here and create a pig head test object, test geometry, display it. And I'm just going to remove the shader. I don't need that. Let's look at this. So I want to convert this to a VDB. So VDB from polygons that we've covered previously. Display this, and I'll increase the resolution in here to 0.05. And the node I want to look at is the VDB analysis. This node, it does an operation based on the sign distance field we're giving it, and it exports a new volume based on that. So the default operation in here is to create a gradient of the sign distance field. So what is a gradient? A gradient is essentially just a normal from the sign distance field. So if you imagine you have a point in here, it will be pointing based on the normal of the geometry. So if we go back to this initial geometry and we just add a normal node and display it in here, and I'll change the add normals to points, and I'll just add a visualizer in here quickly. Visualizer, and I'll go to visualizers and we'll change the attribute to normal, and I'll change the type in here to marker and to velocity trail, or actually just a vector. And as you can see, it's just the direction of the normal from the surface. So what direction the surface is pointing, basically. This is essentially the same thing. The gradient is creating that, but as a volume field, a vector field. As we talked about, directions are vectors, and this one needs a vector to create that field. And we can change that name in here to grad, maybe. Doesn't matter, but just so you know it's possible. And I can show you that we can sample this volume and get the same result as we have on this normal, or close to that result at least. So first I'll just drag a line from the geometry, and I'll just do an attribute create, and I'll create a normal in here, and I just give it a normal is a size of 3 floats. And I'll just keep the values as 0. And the reason why I'm doing that is the geometry by default, all geometries by default in Houdini have internal normals, and they will be displayed if I were to just show you that now. But I want to remove that, so I'm just giving them a value of 0. And now let's sample this volume we created. And as you can see, you can't see that volume. So let's go back in here, and I'll add a point VOP, a vex operator. So I'll connect this in here and display this. This is basically a visual way of coding in Houdini if you haven't done much of that. I'll just write sample normal as a name, and let's go inside. And in here we can read in whatever input we've added in here. So we have 4 different inputs, and it starts with 0, 1, 2, 3. So let's look at that in here. We have these inputs in here, and in order to sample a vector volume, as you remember, this is a vector in here. Let's go inside. You can press on tab and type in sample volume volume sample vector. That will sample a vector volume. You also have a sample, volume sample, and normal volume sample, and that's only for floats. So we're not going to use that right now, but we will use it later. So this volume sample vector, we can give it a position to sample on. This is basically, so we're taking the position of the points on this geometry. Like for example, a point in here would sample the field at this position. Let's display this, and I'll remove the wireframe. So this is the position we're giving it. And in the settings in here, I want to say read in from the second input, because that's the volume we're giving it. And the primitive number we want to read, or the primitive name, we called it grad in here. We can choose a primitive number if we wanted. If you go back and middle click on this, you can see that there is a primitive number here as well. You can use 0. And that's the default you get in here. So that's the gradient, and we can put that into the normal. And as you can see, we got back our color on the pig head. And if we just display this, I'll just do a copy of this visualizer, Alt and drag. So I'll connect it in here and visualize this. You can see we're getting the same normals as we had before. Very, very close at least. Some difference is there always, as the volume is a smooth version of the geometry. You can get closer by adding more resolution. So I'm just going to increase the resolution in here. And if you go to this, it should be a bit closer to this. Yeah. And as you can see, there's difference in length as well. In some places, if you look in here, there's a difference in length. And to get it correct, you can just go inside and just add in a normalized node. Normalized node is basically taking a vector value. A vector value is, as we said before, a 3 float value. Let's say 0.1, and you have let's say 0.8. And then you have 0.1. It takes these values and makes them into a value of 1. Right now, this is a value of 1. But if this was double the amount in each of these floats, it will reduce them to be this half amount to get them to be equal 1 at the end. So it would be something like this plus like this. So that will make the length of these normals the same everywhere. And that should give you very close normals as to what you have in the initial geometry. So that's the gradient. The gradient is basically a normal of the signed distance field, or SDF as we call it. SDFs have a lot of different operators or nodes we can use. So if you write just SDF, you can see we have a lot of VDB SDF operations. You can, for example, go in and smooth this SDF field. If you go in here and put it up here, it will be smoothed, and that will give you a smoother normal down here at the end, as you can see. You can also, so this is smoothing the signed distance field, which we have in here. But when we convert it to a gradient, it's no longer a signed distance field. It's essentially 3 fog volumes. And in order to operate directly on fog volumes, you can use the VDB nodes that don't have SDF on them. So we have a VDB smooth in here, which you can use in here as well. So let's look at the result, and I'll deactivate and activate. As you can see, it's smoothing this one. And we can increase the smoothing if we wanted. Yeah. Hope that's clear and understandable. So the result of this VDB analysis is not a signed distance field. It's usually either a scalar fog volume or a vector fog volume. And you have different operators in here to do different things, like calculating the curvature and calculating the divergence and the curl and so on. I'll show you how the curvature works. So I'll do a copy of this test geometry and put it in here. I'll display it. I'll just add a subdivide because it's a bit low resolution. So I'll just add a subdivide node to add more essentially polygons. And I'll increase this up to 3. Let's convert this to a sign distance field. So VDB from polygons, as we did. And let's increase the voxel size here to something higher, 0.1 for example, to get it very close to what it was before. And I will add a VDB analysis. I'll display this and I'll change the operator to curvature. And as you can see, it's giving us a scalar volume. And right away, we can see that volume in here. It is showing as a ISO surface right now, but that's not a correct representation of this. It's technically a fog volume. Let's change the name to just curve as curvature. And I'll add a point VOP like we did before. And I'll connect this first input in here because that's the geometry we're working on. And I'll connect the second input to where we want to sample from. So I'm going to sample this curvature volume and I will essentially just create a mask using that curvature. Let's just change the name here to sample curve. And let's go inside. And in here, since this is a scalar volume, as we said, this is a float value, scalar volume, we can now use the volume sample and not the vector. We can use the sample. And we're sampling from the point positions, as we said. And in here we can say we want to read from the second input. And we know we only have one volume in there, so we'll keep it at 0 in here. And if I put this directly to the color, you can see we have some form of a representation of the curvature of this geometry. If I just fit this value, so just add a fit, basically take the value and essentially export it as something else, we can see more of these edges. So I'll increase the source max to 2, and I'll increase this source min to, let's say, 1.9. As you can see, we have the edges clearly selected in here. So you can see the edges in here. The edges in here are selected, and so on. And this can be very useful in many situations, both in shading and in creating masks in general. For example, if you have an ocean surface and you have a big wave coming up in here, and you want to have a certain effect on only the top part of the wave, you can calculate the curvature of the surface, and then you can add a velocity force only to the top part of the wave. That's just one example of what you can do with this. You can also, when sampling, if this is too straight and too harsh of a difference between the edge and not the edge, you can always add a noise to the sampling position. So if we add an add node and connect it in here, and then add a, let's say, turbulent noise, for example, and right now this is giving you a float value, but we want to change it to a 3D noise. So it's affecting all of the axes in our position. So right now it's a vector, and we can connect it in here, and it's a bit too much. Let's change the noise type to sparse convolution, and I'll reduce the amplitude by a lot. As you can see, we can affect this sampling position. I'll increase the frequency quite a bit to 10, and let's reduce this amplitude. And you can see we're already breaking up this line we had in here. So we can deactivate this add. As you can see, we're adding more variation to our sampling. So that's the VDB analysis curvature. And you have other things in here to choose from. Great. Now let's continue looking at more volume tools, especially VDB tools. So let's start with adding a test geometry, the rubber toy. And let's zoom back out. And I'll convert this to a VDB. So let's go VDB from polygons like we've done previously. And I'll display this. And let's add a node called VDB combine. So in this VDB combine, you have the ability to combine multiple VDBs. You can either do SDF combinations or just normal fog volume combinations. You can add, you can subtract, you can multiply, and so on. And as you can see in SDF, which we have right now, you can have a difference and intersection. And I can show you what that means by, let's just add a box. And let's convert this to a VDB, like this. And let's connect it in here. And I'll display this. And let's go to operation and let's do VDB union. And as you can see, we have a combination of both of these SDF. And we can move this box around and it will still give you a combination of these two. And what's cool about SDF operations, when you combine them, if you convert this back to geometry, so let's add a VDB, convert VDB, and let's do 2 polygons, you can see that the geometry is one whole geometry, which is great for creating your own custom meshes or just sculpting your geometry as you want. So instead of combining them, we can go and, for example, go for intersection, which will give us the only region that they intersect in. So this is the box and this is the rubber toy. And as you can see in the region they intersect, we get that result. And you also have a difference, which is essentially just a way to subtract using the second input in here. So we're subtracting the region that's in the box. So we can, for example, remove the head in here, like this, and so on. And then we can go on to add another head, for example. Let's add the test geometry pig head. And I'll convert this to a VDB, SDF. And I'll add another VDB combine. And let's connect it like this to take a look. And let's go to operation to be SDF union. And it's combining this result and this result to give you this. We can add a transform just to change the scale and the position of this head. So if we were to scale this down a bit and just move it somewhere around here, like somewhere here maybe. I'll also increase the resolution in here. And that's something important to know. Whenever we increase the first input resolution, by default the second input will be increased to the same resolution in this combine. And you can see that in the resample in here. So B, the second input, is matching the A input, which is the input number 1 or number 0. So if we increase this in resolution, you will get a combination of 2 different geometries, like this. And we can, of course, convert this back to geometry if you wanted. And now we have a different custom shape. So that's the VDB combine. We can also, for example, add a VDB to spheres. VDB to spheres essentially just takes the SDF you have and tries to fill the interior with spheres. And you can choose a minimum size in here and a maximum size and the amount of spheres you want. So let's, for example, reduce the minimum size to something smaller. And let's add more spheres. You can see we are maxing out this shape. This can be very useful for example, doing collisions, because spherical collisions are easier to deal with in many of the collision dynamics we have in different solvers in Houdini. So this is a way to do that if you wanted. And these are just regular primitives, spheres, so it's not a VDB anymore, just so you know that. So this is the previous result and this is the spheres Now let's look at another node. We can add a VDB morph SDF, and we can connect the first input to the result we have in here, and the second input to, let's say, the initial rubber toy we have in here. And let's display this. And the VDB morph is essentially what it basically says. It's morphing between two different SDF volumes. And we can do that based on this time step. So let's delete this channel, and we can increase this. And as you can see, it's slowly fading into the SDF we have in here from this one. So as you can see, you can also go higher in here if you want to get it more closer to the result, and so on. So that's the VDB morph, which can be very useful. Sometimes you'd like to just change the resolution of the result, and there's a node for that. It's called VDB resample. And we can in here use different ways to change the resolution of our volumes. You can either manually type in the size of the voxels, or you can have a scale multiplier. So for example, if we choose this now, we have this voxel scale multiplier. If we do 2, it will be half the resolution it was. If we do 0.5, it will be double the resolution it was, or technically 4 times the amount of voxels. And you can also choose to match to reference VDB. So if you have a different volume you want to match the resolution to, you can connect it in here in the second input. Let's lower the resolution a bit. So let's go to scale and do 2. Let's add a VDB potential flow. This node is, I rarely see it being used by people, but I find it very useful sometimes to get a certain velocity field around the geometry I have. So let me show you what I mean by that. So this, if you immediately click on this, it gives us 2 volumes. It gives us the initial surface, and it gives us a flow vel, which is a flow velocity. As you can see here, it's a vector 3. And that velocity field is essentially the way velocity flows around the geometry. So if we were to have like a wind going this way, and you wanted to avoid this geometry, you can use this node to calculate that avoidance vector. And the wind direction can be set basically by this initial background velocity. And to give you an example of how this looks, let's just add a blast in here, and let's just delete the surface VDB, and only keep the flow velocity. And the flow velocity is invisible, as you can see. And let's add a bound node, which essentially just creates a bound around the volume or the geometry you have. And in here, I just want to scatter some points. So let's do a point from volume, display this. That gives us a bunch of points. I'll lower the resolution by going up in here. And that's fewer points. And then we can use a node we used before, the volume trail node, which takes in a point cloud and the velocity field and displays the trails of the velocity field. And as you can see now, it's going in this way. Let's go back to the potential flow, and I'll just change the direction in here to be 1 in the Z. And if you see closely, you can see how this is avoiding this geometry in the middle. I'll lower the dilation voxels in here so for you to see this a bit better. And yeah, that's giving us a result of avoiding this geometry, which is very powerful and can be used for if you have wind that's hitting collisions and stuff like that. So that's the VDB potential flow. Let's go back to our initial pig head in here. Let's look at it. And I'll actually just do a copy of this VDB from polygons to the side in here. Let's take a look at this. And I also want to show you that we have volume operation nodes These are basically made for the default Houdini volumes, the fog volumes and vector volumes, but some of them can also be used on VDBs. Like for example, the volume ramp, put it in here. Actually, we need to go to this VDB from polygons and change it to a fog to take a look, because this doesn't work on SDF. Display this, and you can see now we can change this geometry or this fog based on this curve or these settings. You also have a volume adjust fog. You can display it, and you can in here, for example, add or subtract or multiply based on a noise or random, or let's do just a constant, and you can see we can multiply the result. And there's a few more of these that work on VDBs as well. I'll show you one more, the volume bop, which is a vex operator. So it's basically a visual way of programming in Houdini. We've touched upon this in previous episodes. And you can connect this in here also and do operations on your volume VDB. This works both on SDF and on fog. So we can, for example, go inside in here, and so you have a density that's connected in and out. You can do operations on this. You can, for example, let's do multiply constant, and there will be a multiplier, and you can add a noise if you want in here, and so on. You can also, for example, sample in this volume again. So if we do a volume sample and make the input be the first input and connect the position to the position, so we're sampling in each of the positions. And now if we connect this to the output, it's the same result because we're just sampling the same volume essentially. What we can do now is we can add a noise to this sampling position. So if we add a node, and we can add a turbulent noise, for example, connect the position in here, and I'll change the signature to 3D noise and the noise type to sparse convolution. And let's connect it in here. And as you can see, it's changing the position where it's sampling from based on the noise. And that will give you some cool distorted effects on your volumes, whether it's a fog or an SDF volume. But right now, we're not seeing all of the fog because it's sampling some regions that are outside of the bounding box of this volume, and it's not able to read anything in there. So to be able to read more outside, we need to just extend the bounding box of this volume and its voxels. So we can add a VDB activate, and you have also a VDB activate SDF if you're working with SDF instead of fog volumes. And we can connect this in here after the VDB from polygons. And right now you can see this is the bounding box. We can go to expand, for example, and we can expand this out, as you can see. And now it's giving us more of that size we need to sample from. So if you go inside this volume bop again, and we can change the settings for this turbulent noise, you can see you can play around with how far it's sampling from. And we can add some more frequency to the noise, for example, and yeah, we can play around with the settings. This is just to show you that you can do operations on volumes in here. And you can take a look at the rest of the volume nodes. Most of the other ones only work on Houdini volumes, but some of them would also work on VDBs. And obviously you have the VDB operations as well that you can look at. Great, I think we'll leave these nodes in here. And obviously all of these scene files will be included if you want to take a look at them. In this episode, we'll look at some fundamental theory about how fluid motion works and how fluid solvers in Houdini works. So before we start splashing around with water, we need to understand how computers actually think about fluid motion. In the world of simulation, there is two different ways to track motion. Let's display them here. We have the Eulerian method, And you have the Lagrangian method. Basically, the Eulerian is a volume-based approach. This is a voxel-based approach, as we've seen before. And the Lagrangian method is a particle-based method. And to understand the difference between them, I'll show you a different way to look at this. So I'll just deactivate this, and I'll open a crowd example that's included in Houdini by default. You can find it in the shelf tools up here. And this is a great way to just visualize the difference between voxel-based approaches and the particle-based approaches. If you were to be using the Lagrangian method, which is the particle-based method, we would be tracking each individual particle separately. So we'd be, for example, looking at, let's say this dude here is Bob. This person has this position, and he has this direction and speed, and he has a color of red and other attributes in him. So we're tracking individual elements and values in this person. And this is a very good way to keep detail in your simulation, to have particles that are separate from each other and they have their own direction. So this guy is going this way, this guy is going this way, and this guy is going this way, and so on. Individual details, basically. And as the information, as the particles move forward, so when Bob moves forward, the information also moves with him. The momentum and velocity is stored, and his attributes of color and other values are also stored with him. So he basically moves as a mass through the simulation. So this keeps detail in the simulation. The problem with this approach is when we try to look at what's happening around the person. So if Bob is running in here, it's hard to know whether he's running into a very crowded region or not by just looking at him. And it's hard to know where everyone else is going in that region around him, and so on. So there's many variables we can't calculate around him through just looking at this one individual particle. You can have Bob just stand there and look at each individual person and record the information, but that is very time-consuming and daunting to do. And that's where the Eulerian method, the voxel-based method, comes in. So if you imagine, instead of caring about individual particles, we care about what's happening inside one voxel at a time. So in this voxel, we see that we have this amount of people or particles, and we can measure their average walking direction or running direction. So let's say their average is somewhere around here or somewhere around this direction. And we can also measure if there is too many of them in this cube, and if they are just pushing too much inside the voxel. So if you had too many people walking in from all sides, you would know that this is a voxel that's getting a lot of pressure. So this voxel approach helps just have a bigger overview over what's going on in the simulation, and helps you also do some more complex mathematics. Like, for example, if you imagine there's more voxels to the sides in here, if there was too many people inside in this box, you could just say, hey, this region doesn't have a lot of people, can you please just go this way, or go this way, or go this way. So we just remove some of that pressure inside the voxel. So this is very efficient to do, instead of having one particle look at the particles around it, which is very heavy, and usually there's a lot more particles than voxels in a system. And it's also good to deal with collisions. So if this guy would be running to a region that is a collision, if there was a wall in here, he would just be pushed back inside the voxel. So it's a lot easier to calculate collisions with it as well. Now, the negative side of voxel-based approaches is that we're just averaging the information. So we're just taking whatever is inside this voxel, and we're just taking the average information. So instead of detailed information about where this guy is going and where these people are going, we're just taking the average of them and saying, oh, they're all basically going this way. And that tends to blur the simulation and give you just a smoother, fluid motion in general. Another thing is that the information inside the voxel is not traveling, so it's not going anywhere. We're just calculating whatever is inside the voxel for every step. So we're not tracking the information over time. So the information also tends to dissipate and blur over time as well. So which one do we use for water? The answer is both. This is the flip method, the flip way of doing things, the fluid implicit particle solver. So that solver is basically a hybrid solver. It uses particles to transfer mass through the simulation and just keep detail in the simulation. Like, for example, if you wanted to have a splash, let's say this is a wall in here. If you were to splash something very hard, you will get individual particles flying off to the sides. So this is very good to keep in a water solver. But also it uses the grid-based method to calculate some heavy mathematics and do some pressure solve and get the fluid to be what we call non-divergent, which we will look at in a bit. Now, besides all of that good stuff with the grids, why else are we using the grids? Let's look at another example and let's jump in. The main reason why we are using grids in the solver, besides the averaging of the velocity, is because water is incompressible. What does that mean? So what is incompressible in this sense? So if you had a balloon, for example, and it's filled with air, and you would push it to the sides, it will compress, so it will be smaller because air is gas, and gas is compressible, so it can make it smaller. But if you did the same thing with water, it would not be possible to compress it because water is incompressible. So the water would be going other places just to not be compressed. So if you pushed it this way and this way, it will just go everywhere else basically to avoid being compressed. And if you pushed it hard enough, it will just explode basically because you can't compress it to a smaller space. So water refuses to occupy less space than it already has. And that's why we need to calculate a way to make the fluid incompressible. If we, for example, had a velocity field where the directions are all going towards a center point in the middle here, like this, then the water would compress in the middle. And this is what we call a divergent field, because all of these arrows are pointing to a middle, so they are diverging into a middle point. And this can't happen in water. So we need a way to solve this. So the way to do this is, if this was pressing in all sides in here, and in here, then this point would be pushing down, and all of these around here would be pushing away to make it basically non-divergent, as we call it. So the fluid is not being compressed at all, so it's moving in here and it's moving out basically. Let me give you another example. So if we look at, let's say we are this voxel in here, and we want to push upwards. So let's say like this. So the velocity is going upwards. And if the velocity of the voxels above it are all going upwards as well, then this is a divergent field because they will all collapse in here. And we can't have that in a water simulation. So what we need to do is to make this non-divergent is to basically move the fluid around. So it's just avoiding to collapse in this region. And this is what we call a divergent free field. And essentially that means the amount of water that entering a single voxel or cell must equal the amount of water leaving it as well. So I hope that's a bit clear on how that works. I'll give you one more example just to show you this a bit more visually. So imagine you have a fluid that's pushing in all directions this way. That fluid would, so let's say we have a wall around here. This right now is a divergent field because it's all pushing in one direction without taking into account the collisions and the divergence in this field. We can see in here the color mapping is the blue is slower particles and the white is high speed particles. So if this was a non-divergent field, I'll just activate this. You would see that the whole fluid has slowed down because you can't just push that much into a wall and keep that speed going. So what it does is it takes the fluid and moves it around, as you can see in here. And it tries to make this non-divergent. And you can see that some places are definitely getting slower speeds in general. It's not a perfect example, but I hope you get the idea of how this works now. Now, when you've done this calculation of non-divergence like this, how do we transfer this information back to the particle? Because at the end of the day, the voxels and the volume is basically just doing the calculation and it's putting the information back to the particles because the particles are carrying that information forward. So there's two ways of doing that. The simple way is just to take whatever information we calculated on the volumes. So these arrows changed in direction from what they were before to this. So we take that information and we just put that as it is in the particles. And that will result in a fluid motion, but it will be very smooth because the difference that was in the particle velocity, so each of these particles probably have their own velocities, is just negated. It's basically removed and we're just adding the average that we calculated in this non-divergence calculation. So that's one way. This method is called PIC, or particle in a cell, and it generally gives you a more blurry fluid. So that's one method. The other method is to take the difference between the initial velocity, which is the initial average velocity of the particles, and the non-divergent velocity, which is a bit different. So you take the difference between them and you add the difference back to the existing velocity that's in these particles. And the good thing about that is that you still keep some of that individual motion and you're getting that averaged motion added above it. So you're getting both of them basically. And this is good to keep individual splashes or individual particles flowing on their own directions and so on. This method is called the flip method. And if we drop down a DOP network, and I can show you this in the flip solver. So if you add a flip solver and we look at the volume motion, we have two different methods in here. We have something called APIC, which is the method I talked about first, which is just takes the average velocity of the voxels and puts it back into the particle, which results in a more swirly and blurred motion. And you have the flip method, which uses the average of the non-divergent and divergent velocity field and adds it back to the particle. And you also have a way to kind of smooth in between that in here. So flip is using both of them basically. So let's just do a quick recap. Basically, particles carry the velocity and we transfer that velocity to a volume or a grid. Then we calculate the pressure or the divergence of this velocity field, and we make it non-divergent, so it's not collapsing in places. And then we add that information back to the particle, and then we move the particles to their new position. So that's basically how the solver works internally. And that's how we get the fluid motion or fluid look in the solver. Great. I hope that's a good overview of this. I just want to mention one more thing. When you calculate divergence, you also get a pressure field. So we know that there is pressure around the walls in here. So if we look at this node that gives us the non-divergent volume, you can see we can output pressure. Internally in a fluid solver, in a flip solver, you get that automatically. But here we can take a look at that. And as you can see, if I were just to turn off the lights, you can see that the pressure is essentially just in the walls and around the walls in here, and nothing in the middle, because the fluid is moving towards these walls. And if I were to add some noise to this direction, just to show you that the fluid is looking different and the pressure looking different, you can see that the pressure is a bit more broken up. I can add some more of that noise to the field, and you can see that. As you can see, the pressure is a bit different now, so there's more pressure on this side, in here, and in here, and in here, than there is in the middle, as you can see. And that's it. Thank you. Now I'd like to show you practically how the flip solver actually is built. So we go from theory to actually building this solver from scratch. But saying that, I'd just like to put a note here that you will probably not need to create any solver from scratch in Houdini in production. And I mean flip solver. You will probably make smaller solvers, but overall you would rarely build a flip solver from scratch. But this is important to understand how things are done under the hood in the solver. And later on we will break the flip solver in Houdini and show you some nodes you can change and tweak for your liking. But for now, we'll just go basics to show you how the anatomy of the flip solver is in its basic form. So let's jump in by creating a geometry node in here. I'll just go inside and I'll put down a dot network. And this will be our dynamic network that we will work in. Solvers inside the dot network usually contains two elements. They contain objects and they contain microsolvers. And we need both of them in this to create this complete fluid solver. To begin with, let's just add an empty object. This object holds the data, so the particles, the geometry, the fields, and so on. But we need to feed it that data so it can basically store it while we solve the microsolvers later. So we know particles are an important thing of a flip solver. So let's start creating a particle field. And you can do that outside or inside this dot network. I'll choose to do it inside. So let's add a SOP geometry and I'll connect it in here. And let's display it and press on P and I'll jump inside. And in here, I'll just put down a box, just a container to add some points inside. And let's add a point from volume, just so we have a point cloud in here. And I'll add the jitter scale to 1, so it's a bit random. We may want to actually lower the separation just a bit. Oh, that's too much. Let's do 0.05. Great. And now we have the particles. We need two different attributes to start this. The first one is the particle scale. So let's add a p scale by putting down an adjust float. And this will automatically create a p scale attribute for you. And I'll just do a scale of 0.05. And the next attribute we need is a velocity attribute. So let's add an adjust vector attribute, And this will create a velocity attribute for us, as you can see in here. But right now it's empty. I'll just give it some initial velocities by adding a noise. And you can press this point trail display to see that there is actually some velocities. I'll keep the settings as they are. This is just the initial velocities for the particles. Let's jump back up. And in here, I would just want to deactivate the use external SOP. So I'm not using an external particle cloud. I'm using the internal one. So let's remove that. And as you can see, we have something right away. Let's remove the particle trails. And we can add the visualization to the velocities we've added. In dot network, we usually add visualizers to just see the fields and the geometry we have and what kind of attributes they have on them. So in here, we can add a particle fluid visualization, this one, and we can connect it in here. And let's press on show guide geometry. And we can see the particles, but they are spheres, and it's up to you what you want to choose in here. I'll do particles, and I'll give them some color. So let's go based on speed, and I'll choose a ramp, and we'll do white water. And now we know we have velocities in here and p-scale, but if we press play, nothing happens because there's no solving mechanism inside in here yet. For that, you need a multi-solver, and this is basically the building block of computing solvers in Houdini. So let's connect it in here and display this one. And if you were to play this now, nothing happens yet. And the reason for that is we need a solver in here, or microsolver, to do the adding of the velocities to the position. We can start by doing that, although we actually need it at the end of the elements we will add later, but we can add it to just show you that this works. So let's add a gas linear combination, which is basically just a node to add attributes or fields together and do some math calculations using this operation menu in here. Let's connect it in here. And what I want to do is, so if you go to this SOP geo where we created the particles, I'll actually just call this one particles. You can see that the data name here, or data name, is called geometry. And this is the default name for particles or the geometry in the simulation in these fluid solvers. So we'll keep it as it is. And we'll go to this gas linear combination, and we will say the geometry we want to work with is called geometry, like this. And the destination we want to add the velocity to is the position. So the position attribute, and the source, what we want to add to the position is the velocity. So it's called V, and we're doing an add operation. Oh, I think we need the position in here and the velocity in here. So we're adding the velocity to the position in here. And we need to multiply the velocity by the time step. So we're taking into account the frames, because there is 24 frames per second, as you can see in here, 24 FPS. So we need to keep that in mind by using the time step. And if we look now, if we play this, you can see we're adding the velocities to the position. So a movement is happening, and there's some form of a solve happening inside the dot network right now. Not much, just throwing the particles in one direction based on the initial velocities we added, but it is a good start. So let's call this one V to position, so velocity to position. That's what we're doing. And now comes the fun part that we talked about in the previous episode, the velocity field that will be treating this velocity attribute we added to the particles in a more fluid way, so we can project the pressure and so on. So let's first create this velocity field by adding a vector field in here. You can either import a vector field, or you can just create one in here. So I'll do a vector field, and the parameters in here, in the data name, we need to call this vel, which is the standard name for velocities in solvers in Houdini, for volumes and fields at least. And you may recognize some of these settings in here. This is the size of the field and this is the division size of the volume. Right now it's 0.1, and we'll keep that as it is for now. Or actually we'll do 0.2 just so we keep it lower as for now. And I want to do the voxel sampling based on faces, as that's a bit more accurate. And then we want to visualize this field by adding a vector field visualization in here, and that's connected to this input. And let's enable this visualizer. Let's go close in here to see what's going on. And I want to add a bounding box so we see this field. So this is the size of the field. And you can go in here and you can see by increasing this, you will increase the size. You can go inside the box we created for the particles and copy the size and put it in the size in here so they are referenced, so they get the exact same size. And I'll show you in a bit how we can resize this based on the simulation. We can also take the initial position, the center in here, and put it inside the center in here as well. So they are connected together. So now we have a velocity field, and you can middle click on this and you can see a velocity field. And if we play this now, not much is happening to the field, only the particles are moving as we had them before. We can start by resizing this field to match the size of where the particles are, which is important because we want to calculate the velocities and the projection of the velocities around these particles. So let's add a gas resize field, this one in here. And I'll actually put a merge so we can connect this and this, and then we can connect them to the multisolver in here. Now, in the settings of this gas resize field, we will have to add the field we're working with, which is the velocity del, and the reference volume or geometry we want to make the volume resize to, and that's the geometry, because the particles are called geometry in here, as you can see down here. So right away, if we just look at this, you can see the field is trying to match the size of the particles. But we want to add some more voxels to the side, so I'll just do 10 voxels to the side. So it's a bit larger than the particles, like this. Great. Now the field is empty now. There's nothing in it really. The particles are just geometry, so the field is something else, and there's nothing in it. So we need to add the velocity that's coming in, or that there is in the particles. We want to add that velocity attribute to the velocity field. And in order to do that, there's a node called gas particle to field. This one, let's connect it. Let's do a merge in here. Connect it like this. And this one has some settings we can set. So we want the destination field, the field we want to put the attribute velocity in is called vel, and the attribute name in the particles is called v, and the particles are under the geometry. And there's more settings in here. The few we want to change are that this operation is happening always, all the time, and that the radius of these particles is uniform. This is just a bit faster to calculate. Now, if we go back and play this, you can see that there is something happening in this field. Let's actually go to the visualization of that field, and let's change the visualization type to speed in here, just so we get some coloring based on the speed of the velocity. And as you can see, the particles are converted to a field, and that's part of the theory we talked about on the last episode. So we converted them to a field, and then as we talked about on the previous episode, we want to do some stuff to that field, and then we want to put the velocity from that field back to the particles. And there's a couple of ways to do that, and we'll talk about that in a bit. So we can put back the velocity that's in this field, and take it and put it back into the particles. And just like we have a gas to particle field, we have a field to particle. So gas field to particle, as simple as that. We connect that in here, and let's see the settings. In here, we want the destination attribute in the particles to be V, and the source field we are sampling from is the vel. And the particles are under the geometry, as you remember. And we want to set this operation always. So now if we just play this, and actually let's just deactivate the visualizer for the velocity field, you can see that the particles are a bit smoother in their motion. When you convert the particles from a particle to a volume field and then back again, then you will smooth the velocity out, which is part of a fluid solver. So we're getting there. Now I just want to add some kind of force so we see more movement in this simulation while things are happening. So I'll just add a gas vortex confinement. And this node just basically takes whatever curling that's happening in the simulation and just amplifies it to a higher value. So wherever there is curl movement or like circular movement, it will just amplify it. And there is a scale in here on how much you want to do that. So I'll just do maybe a value of 5 to begin with, and let's connect it in the middle in here. And the order of this is very important, so you can't just merge them together without following the order. So let's put this before we convert the velocity field to particles, and let's see what this does. And something is happening. Not much though. Let's maybe add more of that and see how that works. Yeah, as you can see, there's motion happening in here, just so we have something to look at. And you can see there's already some form of blurring happening to the particles. So they are getting a bit stringy and so on. And this is coming from converting to a volume and from volume back to particles for the velocity. Now let's take a look at the velocity, and let's play it a bit. And as we said in the previous episode about the divergence and how to get the volume non-divergent, so the velocities will spread out around the field around them. This is a core part of any fluid solver, and we need to add that now. So let's add that after the velocities and before converting the velocity field to particles. And there is a few notes of that. It's called gas project non-divergent, and you have 4 of them in here. The most common ones are the non-divergent without anything else, and then you have the multigrid. The multigrid is a faster method, but it doesn't have as much functions as the old version of this, which is the non-divergent. We'll use this one. Or actually, let's add the multigrid for now. So project non-divergent multigrid. We'll add this first and we'll convert it or change it back to this one later. I'll connect this one and I'll just put it in order before the conversion to particles. As you can see right away, this is doing something to the velocity field. So it's pushing the velocities in places and just activating the rest of the volume around it. So I'll just play this with the visualization, and you can see that how this is affecting the volume around it. And if we were to deactivate the visualizer in here for the velocity, you can see that the particles are moving in a very fluid-like motion, which is coming from this projection non-divergent. And this is kind of really the core of a fluid solver. Now, we talked about 2 different methods of converting velocities back to the particles. One of them was basically just copying whatever is in the volume velocity field back to the particles as they are. This is the method we're using right now, which is called PIC update, which is a particle NSL update. That's the name of it, at least. And we're doing this now, which is basically copying the velocity field back to the velocity in the particles as they are. There's nothing else done to it. But there's the other method, which is called the flip method, which calculates the difference between divergent and non-divergent velocity field and adds that difference to the existing velocities in the particles. So we'll do that now. To do this, we'll need a few fields to be added. We can, instead of creating a field in here, we can use a node called gas match field, which is an easy way to create a new field based on a field that already exists. So I'll just move all of this to the side a bit so we have more space. And let's move this in here. And let's move this in here. I'll call this old vel. We will need to basically create a new field, which is a copy of the velocity field, just so we keep it and use it later to do some subtraction from. So let's call this field old vel. And it's a reference to the velocity field we already have. So reference field is the vel field. And the rank or the type, it's basically a vector field. And we want to match it exactly to the same samples as the one before. I'm just going to give these that are a flip-based method a different color, just so we know the difference. And you can use C to get this menu, by the way. So I'll connect this in here, and I need it to be after the gas resize field, just so we do a copy of the field before we do anything else to the field, the velocity field. But right now it's just doing it's just creating a field without actually adding the values that are in the velocity field in it. So we need to, after we put the particle velocities into the velocity field, we want to also add that information to the old vel. So let's add a gas linear combination. And in here, we want to add some values to the old vel. And the source of this is the vel field, because we add, in this one, we add the velocity from the particle attributes to the velocity field in here. And that velocity field now has information. We can put that velocity field into the old field in here, old vel field. So I'm just going to merge this in here. There's no reason really, just to avoid having many lines going down to this merge. And I'll give it a light blue color. And now after we do all of this stuff with the velocity field, we want to take that information, or the new velocity field that's updated with this these forces and changes of projection. And we want to subtract the old vel from it, so we only have the difference between them left. So let's add a gas linear combination again. Again, this is just a node to do some math. And by the way, I'll deactivate this pick update, or you can add something called enable solver, which will let you activate or deactivate something by going in here. So I'll just deactivate this pick update because we're doing a flip update now. So in this one, let's add, so the destination is the old vel, and we want to take the velocity and subtract the old velocity from the current velocity, and we can use a subtract operation in here. And now that we subtracted that, now we have a field. So the old vel field is basically just the difference between the old velocity and the new velocity that's been projected and has some forces. And now we can add that to the particles. So let's put down a gas field to particles in here. And the source field we want to use is the old vel, because we did some calculation on that. So that's the result of the difference. So we want to use that old vel, which has the difference between the old velocity and the new velocity. And we want to add it to the velocity attribute in the geometry particles. And the operation in here is not copy, but add, because we want to add it above the existing velocity amounts we already have in the attribute. Great, so let's just merge these together, and I'll also make them light blues because they are the flip method, and I'll actually call this flip update, so we know the difference. And we can connect this in here. Now, if we play this, you can see that the particles they do have some of that initial fluid motion, but they also have individual velocities. So some of them are flying away and some of them are doing their own thing. And that's the good thing of having a method that combines both of these methods and adding them together. Right now this is a bit extreme, but you get the point. We can lower the confinement scale here a bit. Let's do 3 maybe. You can see that there is, it's becoming like a sphere of chaos right now, but you can see the initial shape there is, it's a bit more loose overall compared to the smooth pick update in here. And we can see the difference. So if we just add I'll add an enable solver to these sections as well. And I can copy this actually, and I'll paste it in here. And I can do the opposite, just so we can activate and deactivate this one. This one will be activated. And if I enable it, this one will be deactivated, just so we can see the difference. So if I were to run this pick update instead and run this, you can see everything is smooth and slow and a bit more graceful, while the flip update is a more intense method of doing this. And in the built-in flip solver in Houdini, there's a way to kind of smooth between the two and have some form of smoothing on the flip update to get it to be a bit less chaotic as we have in here. Now, the projection method we're using right now is the multigrid, which is not as accurate as the original projection non-divergent. So we can switch it and see the difference. So I'll put this in here, and I'll move this multigrid in here, or actually I'll just remove it. And this projection non-divergent, this requires a surface field, which if you've done any flip simulation before, you know that you get a surface field included in the simulation. So that's needed in here to do the proper calculation, just to take into account the volume around our geometry and to give you more accurate results. So we need to create this field, this surface. So to begin with, let's add a scalar field in here that will be the container for this field. So I'll add a scalar field, connect it in here, and I'll just call this surface, and I'll add a visualization for it. So scalar visualization in here, and I'll just display it as it is. Right now, there's nothing much in that field, but we can add something to it. We can add the particles, basically, the shape of them to this field. I'm going to do that somewhere here before we get to the project non-divergent. So let's add a node called gas particle to SDF, which does what it says. It takes particles and makes them into an SDF field, or a signed distance field that we talked about previously. And in here it's already set up mostly as it should be, or we can take the method and put it to the closest particle uniform radius, which is a bit cheaper and faster to calculate. So we'll do that. And I'll connect it in this merge. And let's actually move it around here somewhere, I think over this oval like this. And we can play and see what we get. As you can see, we're getting something, but it's not moving with the rest of the particles. And I will actually just change the solver in here to the pick update, so we'll get some smoother result. Yeah, so we have a field, but it's only a box in the middle because it's not resized to match the rest of the geometry. So we need to add a gas resize field, this one. And in here we want to resize the surface field, and we want to use the geometry, which is the particles, as a reference. And we can add some voxels to the side. So I'll just do 10, or actually 10 is a bit too much, maybe 3, 3, 3. And I'll merge it with this one, so they are just staying together. And if you take a look at this now, you can see that the surface is following the particles. So we have an SDF field that's representing the particles. And the resolution of this is determined by this division size in the scalar field in here. So if you wanted a higher resolution field, you can do higher resolution in here. And you can see it's high resolution, but it's also slower overall. I'll keep it at 0.1 for now. And at the first frame, it's jumping a bit. I think we can avoid this by going to the scalar field and changing the border type to constant. If we play this now, I think it should be slightly better at least. Great. Now that we have this field, we can go to this project non-divergence and add this surface field. And let's go back to this scalar field, and I'll just deactivate the visualization. And let's take a look at the velocities or the motion of this particle simulation right now. It's a lot more fluid-like and more stringy and generally a bit more stable. Let's change this solver back to a flip solver and update. And as you can see, even the flip solver is calmer and more balanced overall. So this is kind of the core elements of the flip solver, really. So we have the APIC update and we have the flip update, and they both are working right now. I'll give you a few more bits in here that you can work with. If you wanted to add more forces to the velocity field, you can do that in here, like between this section and this section. You can add, let's add a merge in here. You can, for example, do a gas field VOP, which is essentially a VOP field or a VOP network just for fields. And let's add some curl noise, for example. Go inside, we can bring in the velocity field, so bind, and we can write vel. And vel is a vector field. And then we can do a copy of this and make it export to these when it's connected. So it's bringing in the velocity and exporting the velocity. And now we can add some velocity in between in here. So let's drag a line from the position and let's add the curl noise. And we can just basically add it in here. And right now it's just a static noise that's not changing over time. We can do that by adding a vector to vector 4, which will give you a yellow input in here, which means this is a 4-dimensional noise now, which takes into account a time input, which we can connect to the time in here. And I'll just lower the frequency in here a bit, so 0.5 maybe. And the time in here is essentially just the speed of the change. So if we looked at this and played, you can see that there is some change happening to the velocity, as you can see in here. It's perhaps a bit too much. Let's just deactivate the gas vortex confinement, and I'll just deactivate this for a second to see if there's anything happening. So there's not much happening in here, but if we activate this curl and take a look, yeah, it's doing something. So let's go inside and lower the amplitude of the noise and take a look again to see that it's actually affecting our geometry. And you can give it more of that curl amplifier in here. Great. And here you can add the gravity, you can add whatever you want. But if you asked, how can I add velocity to the points instead? You can do that. You can do that before doing any update in here. So we can, for example, add a SOP solver. And let's say we connect it into this input and make it the first one. Let's call this one PTS forces, particle forces, and we can deactivate these two. If you go in here and just add, for example, an adjust vector and connect it in here. And then we can add some, let's say, noise. And let's see if that does anything. So let's play this. As you can see, it's doing something. It's moving in one direction because the ranges are positive. So if we do 0 centered and play this again, they will be centered around the middle. And we can also lower the amplitude maybe. Right now we already have like an initial velocity coming in here. So we can deactivate this if you wanted, just by putting the adjust to constant. And if we play this, we'll have velocities. They should be centered, yeah. So this is how you can add velocities in here. You can even do just a copy of this and add it in here. I'll deactivate this one, or let's keep it on. And let's change this type to constant, and you can add a gravity force in here. So let's say minus 9.8. Let's go up, and you can see right away that the velocity is working. The gravity is working, so it's falling down. So that's one thing. We can deactivate this for now. I'll just activate this gas vortex confinement. And let's change the solver to be a pick solver for now, just to get a bit of a smoother look. And let's just take a look at what we have. Nothing is happening because there's no forces right now. Let's keep the initial force we had before in the initial particles. Let's go to noise in here. Let's look at this. Something's happening. Let's increase the vortex confinement in here to 10. And you can see some strings are happening, which is great. We can actually go to the gas resize field and just add more voxels to the bound so they're not too small. Same thing with the gas resize for the surface in here. Let's just add, let's say 10 voxels. Let's see what that gives us. Okay. One other thing we can do is add more points where there is too few points for each voxel, which is something that's default in the flip solver, in the Houdini flip solver. If you take a look at that flip solver, if you go to the particle motion, you have something called reseeding. So it's reseeding new particles all the time. And this is based on the surface we created. So we can, let's say in the wherever we're creating the surface, we can also add a node called gas seed particles, which will check the voxels and see if there's too few particles in there, and if it is, then it will add more particles in them to make them more dense. So let's connect this in here. And I'll just do, let's say, 8 particles per voxel, and let's do a particle size of 0.1. And let's see how this looks. Let's play this. And it's very dense. I think we might need to lower some resolutions in here. Like the surface, let's go to 0.2. And velocity is fine. Actually, let's change the border in here to constant. And let's see what that gives us. That's looking good. So wherever there is a few particles in a voxel, there will be a reseeding going on that will fill these voxels with more particles. So we're not losing a lot of density over time. And I think that's it for this episode, really. So you're getting the idea of how to create solvers in Houdini, or creating a fluid solver in Houdini. Again, it's rarely that you need to create this from scratch, but you might find yourself adding some of these microsolvers to the existing flip solver. That's very common, and you'll see that a lot in bigger productions. But yeah, that's it. That's how a flip solver works, and that's the anatomy of a flip solver in Houdini. Thank you.